The squeeze theorem allows us to calculate the limit of a function in certain particular cases. This animation represents the squeeze theorem applied to the function f of x equals x squared times sine of 1 over x. As we will see, f of x is equivalent to the function sine of 1 over x that has been squeezed between the two functions x squared and minus x squared. It can be difficult to find the limit of f of x as x approaches 0 using the normal method. That is because sine of 1 over x has no limit at 0. However, Squeeze theorem tells us that the limit of f of x must be 0, because both x squared and minus x squared have limits of 0 at that point. Since f of x is squeezed between these two functions, it too must have a limit of 0. This video is part of a series on calculus, and I also have a calculus book available. See the links in the description below. The squeeze theorem applies in quite a specific situation. Suppose we have some function g of x, which has limit L as x approaches some particular value a. Then suppose we have some other function h of x, whose value is always greater than or equal to g of x, and which has the same limit L as x approaches a. Now let's set a final function f of x, whose value is always between the value of g and the value of h. In other words, f of x is greater than or equal to g of x, and less than or equal to h of x. When we are not close to a, the value of f can take any value between g and h. But notice that as we approach a, g and h get closer and closer together. This restricts the range of possible values of f. We might say that the function f gets squeezed between g and h. Squeeze theorem tells us that the limit of f of x, as x approaches a, must also be L. This is true even if f of x is undefined at a, provided it is defined at every other point in the neighbourhood of a. We can now apply this to our original function, but first let's take a quick look at a slightly simpler function, sine of 1 over x. When x is 0, 1 over x is infinite. What is the sign of infinity? Well, as x increases, the value of the sine function oscillates between plus 1 and minus 1. No matter how big x gets, the value of sine continues to oscillate. It never settles on any one value, nor does it even approach any particular value. We say that the sign of infinity is undefined. Since sine of 1 over x at 0 is equivalent to sine of x at infinity, we can say that sine of 1 over x is undefined at 0. We also know that as x approaches 0, 1 over x gets bigger and bigger, faster and faster. So the oscillations of sine of 1 over x get closer together. In fact, it oscillates infinitely many times as x approaches 0. This means that if we choose any small but non-zero value delta, the region between x equals delta and x equals 0 will still contain infinitely many oscillations. So however small we make delta, sine of 1 over x will not get close to any limiting value. We say that sine of 1 over x has no limit as x approaches 0. Now let's look at x squared sine 1 over x, which we previously called f of x. We know that x squared goes to 0 as x approaches 0. So f of x also goes to 0 as x approaches 0. But it is still the case that it oscillates infinitely many times before it gets to 0. So it isn't immediately obvious whether or not this function has a limit at 0. Now we can make a simple observation. The function sin x always takes a value between minus 1 and plus 1. So of course the function sin 1 over x also takes a value between minus 1 and plus 1. Its behaviour close to 0 is quite strange, but its value can never be outside the range minus 1 to plus 1. So what can we say about the function f of x equals x squared sine of 1 over x? Well, at any point where sine 1 over x is equal to 1, f of x will be equal to x squared. And at any point where sine 1 over x is equal to minus 1, f of x will be equal to minus x squared. These are the extreme values. At any other point, the magnitude of sine 1 over x is less than 1, so f of x will be somewhere between minus x squared and plus x squared. So f of x is squeezed between these two values. Now minus x squared has a limit of 0 as x approaches 0, and x squared also has a limit of 0 when x approaches 0. So it follows from the squeeze theorem that f of x has a limit of 0 as x approaches 0. That is true regardless of the fact that f of x oscillates infinitely many times before it reaches 0. If you enjoyed this video, please like and subscribe. You can also join my Substack newsletter. This video is part of a series covering calculus. I also have a book to accompany these videos. The links are in the description below.